There are two main categories of projections, perspective and parallel. As engineers, we mainly deal with parallel projections. The one depicted here is perspective. You can see how the size of the object has diminished when projected onto the plane of projection. That is the object. Those lines are once again the lines of projection, and that square represents the plane of projection on which we project the image of the object. These are some of the terms that I've written down that will come up during your course, and you must be familiarized with them. And then further under parallel projections, we as engineers mainly deal with multi-view drawings, and they are referred to as orthographic projections as well, because the lines of projections in those drawings are seen as perpendicular to the planes of projection. You'll see an example of that in the next slide. Through your drawing course, you learn techniques and conventions that you are supposed to follow in order to better represent 3D objects as 2D objects. That is basically the entire process of projection. There are conventions to follow, as first a part is designed in your mind, then translated to paper, then forwarded to a manufacturer, then tested. Throughout this entire process, if there is no unified way of communicating what the part looks or functions like, it becomes a very tedious process. You can basically treat engineering drawing like any other language or form of communication that you have learned throughout your lives. As the name implies, in multi-view drawings, we represent the object using multiple two-dimensional views. To make the process easier, we are generally advised to visualize the object enclosed in a box, and all the faces of the box act as planes of projection. So we have 6 principal planes of projection. This object in a box visualization technique is essential to your understanding of engineering drawings. A lot of the intuition further in the course relies on you imagining your object in said invisible box. Unlike multi-view drawings, where the object is strictly reduced to two-dimensional representations, we also have isometric drawings as shown in the figure on top. In the isometric drawings, most of the object features are defined in this singular view, and in that view, the object is still represented as a three-dimensional object. You can see that in the multi-view drawing below, the object is represented in 3 of its faces: the front face, the top face, and the right side face. It is information from all these 3 faces together that gives us an overall idea of the object's shape. The drawing done in the picture below is following the third angle projection convention, where they use the front, top, and right side views as depicted in the diagram. The symbol in that diagram represents the third angle projection convention being used. There is also first angle projection convention, but we generally do not study that in North America. This is the isometric view of a part I designed in SolidWorks. I have rotated this part around the y-axis so that you guys can better understand the shape of the part and then visualize it inside an invisible box. Then you can try to unfold that box and try to get the 6 views of this object inside that box. I have also attached alongside the isometric view an animation of the box being unfolded with the respective orthographic drawings. Hopefully by this time you have a better understanding of what visualizing an object inside an invisible box looks like. We see that 3 of these views are redundant, that is, a lot of the information is overlapping between multiple views. It is generally the case that we are able to describe an object in less than the 6 views that are available to us in the invisible box. Throughout your course, you will generally find that 3 views are more than enough to define most parts or objects that you'll find around you. Some simple parts like primitive solids like a cylinder, cuboid, and the sort can be even defined in two views. So now I'll erase the redundant views and try to keep my drawing in accordance with the third angle projection, where my choice of the front view is arbitrary and the top view is above it and the right side view is to its right side. The plane of projection corresponding to the top view is the horizontal plane of projection, and the plane of projection corresponding to the right side view is the profile plane of projection. The plane of projection corresponding to the front view is the frontal plane of projection. These terms are used interchangeably with top, front and right, so there's no need to be confused when you come across these words in the future. The invisible box is three-dimensional. If you keep one corner of the box at the origin of a three-dimensional coordinate system, you can rationalize the 2D-ness of each of the views with respect to the two axes that change on them. The x, y and z axis in this case basically represent the width, the height and the depth axis of the object respectively. Take for example the top view in the first diagram. You can see that the x and the z axis are changing in the top view. Now if you visualize that object in front of you inside a box, you can see that only the width and the depth dimension are changing on the top view. A lot of the intuition in understanding technical drawings can simply be attained by seeing the methods you learn in action. Here, seeing truly is believing. The best way to do this is to create simple parts on CAD and observe their views. We have now the same part from before enclosed in a partially opened box, and then the exploded view of all of its 6 views. You can clearly see the width, height and depth relations and how they are related between the various views. This now brings us to the first and most important rule of projection theory. You can see that feature in one view lies on the same parallel projector in its adjacent views. To further understand this idea, I create a parallel projector between the top, front and bottom views, and we see that the whole is aligned along the same projector in all the 3 views. We can similarly extend this idea to any of the features among any of the 6 views. When the box is closed, you can see that even the depth relation between the top and the right side views can be extended using a parallel projector. But when the box is unfolded, we see that there is a discontinuity between the right side and the top side. Now, you might ask yourself, how do we transfer the depth dimensions now? Or how do we establish a relation between the feature in the top and right side views? There are 2 known methods. One is using a miter line or a 45-degree line between the top and the right side view. And the second method is to use your compasses. The use of the compasses is fairly intuitive if you've got a hang of the invisible box visualization now, but it is put into better words using the second rule that will be coming up in this lecture. In the upcoming clip, I have attached how to use the miter line or a compass to transfer the depth dimension between the top and right side views. This is a fairly important technique, and it's better if you make it mechanical at the start of your studies of technical drawings. Here we have 2 views of the same object that we have been seeing till now, and we are asked to create the third view using the various transfer methods that we have learned up till now. I will not be completing the missing view. I will only show you how to transfer the dimensions between the top and right side view, but the third view is available in this video if you scroll back. The completion of the third view is left as exercise for you, the viewers. The feature in discussion is on the part of the part where there is no hole and the inclined face starts. The pink feature, I project it using a parallel projector from the front view to the right side view. And then that same feature I project from the top view to the miter line. And from the miter line I project it downwards into the right side view. Where both the projectors intersect indicates the position of that pink feature in the right side view. This is consistent with the rule 1 that we studied, and also for you visual learners out there, it makes more sense when we close the box and observe the feature in the top, front and right side views. We also know that the top and right side view share the depth dimension, and since the same object is being depicted in the top and the right side views, we can make an educated guess that the depth of that feature in the top view will probably be at the same depth in the right side view. So what we do is we take its depth using a compass or a pair of dividers from the top view, and then that same depth we transfer onto the parallel projector that we had drawn from the front view. We see that this is still consistent with the point that we had projected using the miter line. For those of you confused still about what a miter line is, it is a 45-degree line that we have constructed to the intersection of the folding lines that are present on the front view. The folding lines represent the folds that we see on the box, the seams where we bend a piece of paper to create that invisible box. The miter line is just a handy technique, a handy convention used to transfer the depth dimensions. You can see how helpful the isometric view here is in visualizing the object and then transferring its features between the various views. If that isometric side on the right was not present, this would have been a much harder task to complete. I might start to sound like a broken record by this point, but it's really to drive home the point regarding how important this box method is to your intuition and understanding. It's good to know what your folding lines represent with respect to your box, how you are supposed to visualize the different views, how to choose the different views that you're going to draw. The choice of the front view is arbitrary and the top and right side view are constructed around it, etc. This is the more intuitive way of looking at the box method of visualizing an object. One term that I'll introduce you guys to is related views. These are two views or projection planes that are adjacent to the same view. In our example, which is generally put in the third angle projection, we see that the top view is adjacent to the front view and the right side view is adjacent to the front view. So now you can say that the top and the right side view are two related views. When you're looking at this closed box, you can see that both the top and right side views share the variations in the depth dimension. This brings us to rule number 2. If you observe the same feature in both the views, in related views, what you'll see is that the feature in both the views will lie at the same depth. See, it could have been the left side view, the bottom view. Since all of these views are related, all of them are adjacent to the front view. To measure the depth, you will get the distance from the folding lines or the reference line. In this example, I will observe the feature that was in discussion in the previous slide, the pink feature. We see that it is a distance d from the folding lines in both the top and the right side view. The distance d represents the depth of that feature in both the views. We have not really worked with curved paths up till now and how to represent them in our drawings. A regular curved solid is represented by its limiting elements or visible boundaries. I will now show you some curved solids along with their top views. For simple curved solids, the projection can simply be thought of as placing the solid in between a flashlight and the plane of projection, obviously with parallel lines of projection. But with more complex shapes like the cylinder on the right, it is back to the invisible box. Again, it is only from the isometric views that you know this is a cylinder. One two-dimensional view does not give you enough information to infer that the object given to you is a cylinder. If you are only given the top views that are shown right now, you could very well reason that the object on the left is a cuboid. I'll also trace out the top view for the object on the right as well, so that you guys have a better understanding of how to draw these objects. We now move on to a sphere, and to no one's surprise, the front, top, right, bottom, any view of the sphere will obviously be a circle. To practice your understanding, I'd ask you to cut the sphere here, like the cylinder example, with the plane parallel to the top view, and try to visualize it. Here it is more of a test of how you can convert the information given to you regarding the object in 2D into a three-dimensional shape of the object. You're only given the top view, no isometric view or other multi-views. I'd like you to visualize what would be the correct object for this given top view. As you can see, there is no one correct answer. The lines in the top view represent changes of plane, and you can see the planes can be at different inclinations, different height, they could be curved, and they still give you the same top view. In an introductory course, you'll generally be asked questions where you're given two of the multi-views and you're asked to draw the third view. To solve these types of questions, you'll take advantage of the visualization techniques you've learned and the two transfer techniques that you have learned with respect to the first rule and the second rule. If you're able to have a general idea of what the object is supposed to look like, with the information from the two views, you'll be able to extract the third view as well. Before starting off with any of these questions, I make sure to draw out my folding lines. The position of my folding lines are arbitrary because they're just used for reference. Like, what use to you would a coordinate system be if you didn't have an origin to use as a reference point? So just make sure that the depths from these folding lines are same in the top and right side view, otherwise their position is arbitrary. I just drew them one square away from my views because I'm limited by the space I have in my predefined grid. I have now established my folding lines or my reference lines. The next plan of action for me would be to draw out the miter line at the intersection of the two folding lines. It's just a 45-degree line from that intersection point. You could either draw the miter line or use the compass method as we have stated before. The compass method will be more important when we start dealing with the auxiliary views and descriptive geometry, because there are just some cases where you cannot use a miter line because the two views aren't as conveniently placed as the top and right side view. So just have the intuition regarding the related views sharing a common dimension and how it can be transferred uh, in your mind whenever you're transferring dimensions. Like, whether it's asked or not, just remember to visualize that object in a box. That is the most important tip that I can give to you guys. There's just so much information in both the folded and unfolded views of the box. In my diagrams, since you're starting out drawing with technical drawings, I have labeled the projectors from the front to the top view with letters, and from the right side view to the top view with numbers. This really won't be necessary once you're more accustomed with drawing the missing views, but since this is some of y'all's first time dealing with drawings, I'd really recommend labeling them out. I think for me it will be easier to start my drawing off using that slanted face, since we see that the face, the U-shaped face in the right side view is seen as a slant edge in the front view. So since it's slanted, we'll be able to see that face in the top view as well. So what I do is, you see the higher point of the slanting face, it lies along the projector A, and in the right side view we see that that line is present at 2 points on the projectors number 2 and number 5, the intersection of projector A, projector 2 and projector 5. What this intersection will give me 2 points which will join together to form the top edge of the slanting face. I try to transfer points of all the remaining faces. You can clearly see that the object inserted into the slanting face is sort of a cuboid, so you'll see its top face in the top view. There are three main faces that you'll see in the top view. One will be the slanting U, one will be the top face of the cuboid intersecting that slanting face, and one is the square base. You can tell it's a square base because the base is 5 units wide in the front view and 5 units in depth in the right side view. If there was nothing intersecting the slanting face, you would have not drawn the line between the tips of the U, but since there is a cuboid inserted into that space, when you visualize it, you'll see the top face at that point. After drawing out the cuboid and it intersecting the slanting face, I then draw out the base. To make the top shape clearer, I'll now draw its outline using a pink highlighter. You just have to remember, throughout this whole process, I had a rough idea in my mind of what the shape would look like from the top, from the information I had regarding the front and the right side views. That is a must. Whenever you're dealing with these missing view questions, it is a must to have a rough visualization of what the object is, because the two views give you enough information to draw out the object. That means you have enough information to visualize the object in your mind. After I'm done with the top view, I now try to compare it with the image I had in mind. Does this top view correspond to the image I had of the object in my mind? That is another question I have to ask myself. Now I show you the various faces that I have represented in the top view. I could have also marked A along the slanting edge in the front view, but since we can see it as a face in the right side view, I opted to do it there. I did not use any complex examples in this lecture. We haven't really dealt with hidden lines and other more specific features like holes, ellipses, and other constructions. I just wanted to keep it simple and to the point. These lectures are really supposed to complement your courses at whatever educational institution. Mm, uh, since this is my first lecture of these sorts, there might be a lot of mistakes, and I'm very happy and open to feedback regarding this. um, I'd like to leave you guys on a very simple note. I would really love, like, it would be in your greatest interest to just practice, practice, practice. That's what engineering drawing is about, practicing it until the drawings become second nature. uh, you all probably have assigned textbooks. I'll try my best to assign a PDF of some problems in the description. On that note, be hoping to see you guys in the next lecture. Have a great day.